Hello, good afternoon, everyone. So thank you very much for joining us for this online meeting on photonics for space, and we'll focus this our discussion of today about extreme environment. So I'm Jérémy Picot-Clement. I'm a technology specialist at Optikk in charge of space topics. Before to start, I would like to thank our sponsor of the today's event, Photon First. So thank you very much for this. And yeah, before to start, I would like to give the floor to Photon First to present their slide, and then we will start the meeting. So you can start and take the floor, Matthias.
Thank you very much. Good afternoon, everyone, and thank you for the opportunity to talk here today. Brief introduction, I'm Matthias Kahl. I'm a sales engineer for PIC packaging at Photon First. And today I'd like to briefly talk about a topic that's becoming more and more important in photonics, and especially in photonics in space. How to turn a PIC from a fragile laboratory component into a reliable system that can actually survive and operate in harsh and extreme environments. In many cases, designing the PIC itself is only the first part of the challenge. And once you start looking at space applications, you very quickly have to think about shock and vibration during launch, thermal cycling, radiation, long operational lifetimes, and last but not least, maintaining the stable optical performance of PIC under all of those conditions. This is really where packaging becomes critical. Now, at Photon First, we have been working on PIC packaging and photonic system integration for more than 20 years. We are based in Alkmaar, about 40 kilometers north of Amsterdam in the Netherlands. And our work covers the full chain from the package design, fiber alignment, electronics integration, testing, qualification, but also production engineering. Now, one thing we often see is that packaging still is sometimes treated as the final assembly step only. But especially in space applications, packaging has a direct impact on the reliability on the system performance. Bare PIC die is extremely sensitive, and even small mechanical shifts or temperature effects can influence the optical alignment and therefore the entire behavior. A good package is therefore not only here to protect the chip mechanically, but it also has to provide thermal stability, robust electrical interconnects, stable fiber coupling, that's crucial, and a structure that can survive harsh environmental conditions over time. Now, another trend we see is very clearly is the increasing complexity of PIC systems. For example, also in quantum and sensing applications, the fiber array counts are growing rapidly. Electronics integration is becoming more and more dense, and the thermal requirements are becoming especially demanding. Now, at that point, the packaging becomes a real engineering challenge. Our work therefore includes the custom package development for diverse applications, the precision die attachments and bonding, wire bonding, ultra-stable fiber alignment, EMI shielding, thermal management, and qualification-oriented assembly processes, which also includes a full traceability and documentation of these. Now, for the optical alignment stability, for example, we use laser welding approaches designed for the harshest environments where vibration and especially temperature changes are major concerns. And qualification thereof is also a large part of what we do. So we are very experienced in thermal cycling, shock and vibration testing, EMC testing, accelerated lifetime testing, but also radiation and testing of PICs and the ready packaged systems. Now, some of this work has been carried out together with our partner organizations such as STEC and NLR in the Netherlands. But an important part for us is that we are not only packaging devices for customers, but we also developed and qualified our own PIC-based systems for harsh environments, which gives us the practical experience with the full process from the assembly via qualification, manufacturability, up to the long-term reliability. So as a conclusion, for space applications, the PIC performance alone is not enough. And the real question is whether the system remains stable, reliable, and also manufacturable under those real operating conditions. And this is exactly where we at Photon First aim to support you as our customers and partners. And here's how I want to conclude my speak. And thank you very much for your attention.
Thank you, Matthias. And if you have any question, do not hesitate to contact Matthias during the meeting using the chat, or you can also contact the Optikk team, and we'll be pleased to do the introduction. So thanks again for sponsoring the event, Matthias. A few words about Optikk before to start. So Optikk is the largest industrial network in the world in the field of photonics. We have today more than 850 members. We cover all the value chain, the photonics industry, from component manufacturers to design and prototyping company to also end users and system integrators. We also cover all photonics application, so from space as we do today, but also including AR, VR, agriculture, PICs technologies, laser technologies, and also quantum topics. So it's quite wide, and our aim is to create a sustainable European photonics industry, as you already know. What we provide to members, so technology support, market and technology report. So you have access as a member, as an Optikk member, you have access to this networking event, access to market if you want to explore Asian market or US market, North American market. We are here to support you, mentorship, and also HR support. And for companies which need investment, we are also here to support this part of your journey. Few words also about the next Optikk event we organize. Firstly, in-person meeting during the year. So we'll have an Optikk meeting on optical fiber sensors at Airbus in Germany. Then in June, something that could interest you, an Optikk technology meeting on photonics for space and new space at AIP, Potsdam, Germany. So you are more than welcome to check the website, check the agenda, because everything is ready. Also the company visit. So please have a look, and if you want to join, you are more than welcome to come, of course. Then we'll have a meeting on photonics for quantum technology at SEDI-ATI. We also have a plan in September at CIOE, Tech Watch, also for ECOC, and then we'll have a tech session on photonics at Quantum Effect. A few words also about online meetings. So we cover not only technology, but also marketing, HR, communication, sustainability. So it's quite wide. So I'm pretty sure that you could find something interesting for you here. So please have a look on the website, Optikk website. Yeah, so as I said, we cover all the value chain. So today we have company from the integrator side, from the R&D side, companies that are making components and modules, equipment manufacturers, also companies that are making materials, contract manufacturers and foundry, software and design, very important also for the value chain, and yeah, of course, metrology and testing and service providers. And now, just to give you a short overview of the agenda of today's event. So we'll have the first speakers, Anna Pogrebna from Menhir Photonics, your strategy manager. Then Johan Bauwelinck from imec, professor. We'll continue with Amandine, Debouldts, marketing and communication manager at SEDI-ATI. Lars, Lierstuen, head of space and business development at NEO. Then Juan Barbero, Optoelectronic department at Alter Technology Group. And we'll end this meeting, if Roman is able to join, with a tiny telescope, a presentation by tiny telescope. So thank you very much again for joining. You will have time to ask any question you have after each talk. We reserve 2-3 minutes for questions, so feel free to raise your hand through Zoom to ask any question we have during the meeting. So thank you very much. And now I give the floor to Anna from Menhir Photonics. So Anna, if you are here, you can share your screen and start your presentation.
Thank you very much for the introduction. I'm starting the share. I think now you should be able to see my presentation, right?
Yeah, all good.
Okay, thank
Thank
you.
you.
Hi everyone, thank you for coming. So today my presentation is going to be about laser frequency comb for space applications such as synchronization, RF and ADC applications. Just a little introduction of our company. I'm from Menhir Photonics. We are a Swiss-based manufacturer of very precise lasers with production facilities here in Zurich, around 40 people in the company. And we are selling our lasers all over the world, already in 17 countries. And our main focus is on delivering something very robust and for harsh environments, as the topic of today's meeting is. So few details about the product itself. What we do, we make pulse lasers that make pulses on very organized manner with extremely low phase noise from each other. We work in telecom wavelengths on 200 to 10 gigahertz, from 200 megahertz to 10 gigahertz repetition rates. Why it's good, this kind of technology, because of this extremely low phase noise, it enables multiple different domains that are also space relevant, such as optical communications when you want to make link from Earth to space, for instance, for low noise RF generation, for also the timing distribution mostly, or also for very precise ranging that is also very relevant for space. Our type of technology is not in space yet, but we are known for making something very robust, like on the market. Already from 2023, our laser was not even ruggedized laser, was on airplane, just like that, on the rack, measuring methane gas distribution across Europe. But why I was invited to talk today and why we are relevant for this meeting is because we started the project a bit more than a year ago in collaboration with ESA and CSCM, that was funded by Swiss Space Office, to develop a space ruggedized mod-lock laser that would be mostly used for communication and timing synchronization. And together with ESA, we drafted the requirements that would make it eligible for low Earth orbit flights. And the first prototype is already going to be delivered in a few months. So this is our roadmap. Our company exists since 2018, and we are already known on the market to provide the best performance on low noise optical oscillators. Now with this ESA-funded project SparkCom, we are getting close to delivering the prototype that would be ready for space. And we are getting ready for 2029 to be ready for the in-orbit testing. Another key feature of our company and of our production capabilities that is not directly related, but we're also putting big focus on high volume production. We want to be the first company that would produce ultra-fast lasers on tens and hundred thousands of units per year with automated production. So I was asked by Optikk to say what we offer, but also asked to the community what they have. So as I have mentioned, we are offering the space ruggedized frequency comb, getting ready for the orbit demonstrations. We offer the lowest phase noise on the market for anyone who is interested in extremely low noise RF generations for synchronizing anything on long time scales. What we are looking for is a few things. Of course, by 2029, we are looking to join some mission with optical payload, as well as system integrators, people who developed miniaturized optical clocks in high volumes, RF and timing, inter-satellite links, not QKD, but like wherever you need synchronization, ADC or spectroscopy. So that's the type of collaborations we are always on lookout for. Thank you, and please feel free to reach out by email or just check our website.
Thank you, Anna. Thank you very much for your presentation. We have a question from Alkma. Alkma, you can ask your question.
Hi. Sorry, one second. Mute, please.
They are in the same room, that's why there is an echo.
Let me try. So the question was...
That's good.
Here you go. Let's try now.
Yes, we can hear you, Mirve.
Let me try muting here.
Okay.
No, we can't hear
Now
you.
you're totally.
Hello?
Now.
Yeah.
Okay, finally, we never get this right. Why did you select the butterfly for going to space, the butterfly model package? It's a very curious choice.
No, that's not for... Butterfly is not for space. The one that I showed for space, it's gonna be like this. Of course, butterfly, it's not there yet. We don't produce butterfly yet. So our product is usually like shoebox size. Next year we're gonna be producing something like a small calculator, and that's more or less the size that we're gonna be able to send to space. So like small satellites are not big enough for our type of device, but it's gonna be something, I don't remember, I think they said it's gonna be 1 kilo. This unit, more or less, maybe a little more than 1 kilo, and a few centimeter big, and 10 by 17 centimeter, I think.
Okay, thank you. Do feel free to reach out to us if you want to shrink it further. Thank you.
And the butterfly is to give a cookie to Earth, to the ground applications.
Thank you.
Okay.
Thank you.
Thank you.
But getting
Anna,
the butterfly is gonna...
yeah, your connection is not very good. Maybe you can switch off your camera.
Thank you. We will. Definitely.
Okay, there is a delay. Okay, any other question for Anna? And if not, let's thank Anna again, who left, but she will come back. So thank you, Anna. And we can welcome our next speaker. So welcome, Johan Bauwelinck. Johan, you are professor at imec. So welcome, Johan, and please, the floor is yours.
Thank you, Jeremy. Do you hear me well?
Yes.
Ah, excellent. So good afternoon, everyone. So I'm Johan Bauwelinck, part of imec and part of university. And in this presentation, I just want to give you a quick snapshot on what we do on optical transceivers. Just checking my screen sharing is, yeah. So on all the technologies and designs that we make for optical transceivers to be used inside satellites. So I do have a bit too many slides, but these might be useful for your reference. So I'll first very briefly situate our work, show a few examples, and then explain a bit about the technologies that we believe might be valuable for you in order to design your own high-speed electronic or photonic solutions, and what type of architectures could be used today. So our work is situated in the global communications infrastructure where satellites play an increasing role for 5G and 6G. And more in particular, the part that we focus on is situated inside the satellites, connecting, as you see here schematically at the top, connecting the transmit and receive antennas. So inside the payload of a satellite, these antennas are connected, and in between there is some frequency translation being done, or maybe a bit of signal processing. But basically, in its simple form, it's just like a low noise amplifier, a power amplifier, and in between, some mixing. Now, the limit today is that these are connected through bulky waveguides or thick coaxial cables, and these are kind of heavy, of course, and they have some high frequency losses. So that's why we would replace these with the blue lines, which would be fiber optic. So then there are basically two approaches. Either you just take your analog or RF signal as they are and you transport these optically, or you digitize these. So both schemes have their pros and cons, but without going into detail, both are currently still being developed and considered. The digitized gives a bit more flexibility in processing. However, it's a bit more complex because you need high-speed RF ADC and DACs, while the analog way, well, it's analog, so it introduces its distortions and you need to be quite linear along the way. And the mixing needs some particular solutions. Like for that purpose, we, for example, look at optical phase lock loops, optical alloy distribution, and such things. But nevertheless, both consist or are still being considered together. Just to sketch a bit the idea of what we develop. So this was an example of a circuit that we developed together with Embryonics and ESA. And this was looking at a digitized solution for radio over fiber. So this is the schematic of an electro-absorption modulator driver, which for which we co-designed the electronic and photonic chips. So here you see our electronic chip. It's in red-hard 130 nanometer SIGA by CMOS technology, fabricated by IHP. And the biggest chip at the top, this is imec silicon photonics, where you see 4 modulators, and at the right-hand side, the optical connectivity. And you see from these eye diagrams that this works quite well. Because this was our first real red-hard design in our team. imec Leuven has more experience on red-hard design, but they have less experience on high speed. So for high speed, this was the first one. So for that purpose, just to show that we did our work properly, we also went into the radiation testing. Here we see the TID measurements where we see very little degradation, up to something like 1.2 megarad. And this was the limit of our beam time at that point. And then we also went into heavy ion testing at Louvain-la-Neuve. And it's really fun to see how a heavy ion or a particle can cause bit flips. So the dip you see here is actually strong enough to change a 1 into a 0 bit. And by counting these, we could assess the radiation tolerance. So I would skip this comparison because at this point, this is not so important to you, just to show that power consumption is one of our main goals here. The RF type of solutions, where we don't need to digitize the signals, are displayed here. So on this chip, we have the left and the right half. So one is used for transmit, one is used for receive. Then we also made the corresponding photonic picks through the Mach-Zehnder modulator and the germanium photodetectors. So these were considering K and Ka band. And in this co-design, we also take care of the biasing and scalability to more channels if needed. And these chips are now used as workhorse for the next steps, considering also frequency translation. Some very nice pictures here. So at the left, we have the transmitter side, so the driver with the Mach-Zehnder modulator. And here at the right-hand side, the receiver with the photodetector. In terms of linearity, things look very good. And in terms of frequency response as well. So now the next step is to do the radiation testing of these devices. If you want to know more, this work was published at UFC this year. What may be more generic and more useful for more people online is how we design these things. Electronic and photonics so far have often been designed separately, however, considering their impedance matching. Nevertheless, a co-design can go further than this. And first of all, in order to do a good co-design, you should be able to co-simulate everything. And for chip design, Cadence is still the main platform because electronic chips are quite complex. And together with Cadence, we worked on their electro-optic simulation capabilities. And here you can see how these are combined together. Basically, this reference listed at the bottom is wrong. I will replace it with the new version that will be shared with you because it was designed at Cadence Connect, since this was a collaboration. And in this way, you see that the simulated electronic chips, photonic chips, and wire bonds and assembly parasitics or EM models can nicely be combined. Also, what you see here at the bottom in the schematic, you then also have light signals with this laser. So this is actually quite powerful in terms of environment. The pictures you saw before, this was our prior work, which we have developed in silicon, but we're also starting some new things. I have some colleagues on quantum, but this is not included here. What I'm personally managing is basically our next high-speed development, where we look at 4 times 100 gigabit per second for the same application in the frame of an ESA project together with embryonics. Again, since there are no standards in space, we would take advantage of the possibilities. However, we should also look at what is offered by Datacom terrestrial in order to take advantage of what's available and also take advantage of the knowledge we build up so far on terrestrial applications. Nevertheless, all with the objective of very low power and compact integration. In terms of technology, we would be considering more like Global Foundries have the SOI technology, because at imec there is a very big team working on the DARE platforms. The DARE platform is actually providing PDKs for foundries which take radiation into account. So you could have digital cells which have been radiation hardened. You could have simulation tools in order to simulate what happens when an event happens. You could indeed assess reliability and so on. Furthermore, of course, since we are imec, taking advantage of imec silicon photonics is also one of the things we often do. And imec basically has one of the most complete platforms available, as I will show in a few slides. So if you want to know more about the electronic technologies, you can read the slides later on. It's maybe more important to show how well advanced the imec platform is today in terms of photodiodes, different types of modulators and bandwidth characteristics. And this is ideal for developing radiation-hardened transceivers, where you can then think about scaling to many channels or thinking about redundancy in your architectures and so on. Furthermore, the imec platform is fabricated on different lines. So the 300 millimeter line is in Leuven in Belgium, if that would be of importance for your application. We did not assess the radiation tolerance of the photonic devices ourselves so much. However, there are quite some groups who did so. So that's why I list a few publications here that might be of interest to you. So here, for example, we have some work which was done in the frame of the radiation of high energy physics experiments, where the requirements are different from space. However, they also did a lot of experimental work on silicon photonics, because in these particle experiments, they do need to gather more and more data. For that purpose, they are also considering or actually moving into silicon photonics. Furthermore, with silicon photonics, you can have the light source out of the radiation chamber so that you can have keep your light source safe and put the modulators and detectors in the extreme environment. Here we see two measurements of Mach-Zehnder modulators, ring modulators. I'll not go into details. Here we see different photodiodes. All have been assessed through a large extent. And here this is some work done by Santana on the design of a new Mach-Zehnder modulator, where yes, TCAD simulations were done to show basically how this works. And the person that did this work at Santana is currently part of my group as well. So, and with this very quick walkover, I can wrap up and listen to your questions and discuss about this work. So basically in my team, we mainly look at the radiation-hardened high-speed transceivers, but we also have colleagues here in the group who work on quantum type of solutions or photonic ADC type of solutions. So also on that we can chat a little bit. And apart from that, well, technology is important today, considering the complexity, challenges, and geopolitics. But also, besides technology, we also think about new architecture in order to bring additional functionality in our applications and think of co-design and co-simulation. So with that, I would like to thank you very much for your attention and thank you very much for the opportunity to speak here and engage with you.
Thank you, John. Thank you very much for your nice overview. Do we have any question for John? Can you raise your hand through Zoom? John, about your 112 gigabits driver, do you expect it to be more or less sensitive, to space radiation compared to your older generation of drivers?
That's a good question. Do I have my backup slides here? Because it kind of, let me see. Let me try to share this slides. I will just unhide my backup slides and there we can talk about technologies. Yes. So basically, well, in terms of technology, I believe the FD-SOI technology platform will allow us to reach similar performance in speed and tolerance because, well, first of all, FD-SOI itself has some good performance, plus we would have the PDK with good design rules, additional ways to check tolerance. So there might be also some further interesting points. So on this graph, you do see that where is my pointer? Yes, you do see that the silicon germanium and the FD-SOI are pretty close together in terms of performance. They are both very suitable, both for high speed and satellite applications.
Interesting. Any question for John? And another question from my side. It's very interesting. What is the most challenging part, about packaging your chips to make sure that they will survive, the temperature swings in space? What is your main challenge?
That's a good question. I think there might be people online who know more about that because on packaging for these extreme environments, I'm sorry, I'm not into that myself. But good question.
Thank you, Johan, for your presentation. Thank you very much.
Thank you. Let me stop sharing here.
So
I need to press stop sharing somewhere else.
Thanks.
Thank you.
So now let's welcome our next speaker, Amandine. You are a marketing and communication manager at SEDI-ATI, and you will talk about optopyrotechnics for launch vehicles, critical function on the ground and in flight. So please, Amandine, the floor is yours.
Yes, thank you. So let me share my screen. Do you see the screen?
Yes.
The
Good.
slides, okay. So good afternoon, everyone. As part of this EPIC Online technology meeting on photonics for space, extreme environment, I will focus on how optopyrotechnics enables critical functions in launch vehicles, both on the ground and in flight, and with an emphasis on extreme environmental constraints. So I will use the Ariane 6 as a concrete example throughout the presentation. The key message here is simple. In optopyrotechnics, photonics must remain fully functional in some of the harshest environments encountered in engineering systems. Just before going further, let me briefly introduce the company. So, Fiber Optics Group is a global leader in fiber-based photonic solutions. It is quite a new group as it was created in 2023. And today, the group unites three high-tech companies, namely SEDI-ATI, Ideal, and Fibertech Optikk. These companies are specializing in photonics with a broad offering from the manufacturing of custom fiber-based components and complex assemblies to high-end optoelectronic systems and smart integrated solutions. The group serves high-tech industries in defense, space, aeronautics, quantum, and energy markets, just to name a few, and where systems must operate reliably in extreme environments. Actually, the group's headquarters, as well as two of the subsidiaries, are located in France, one near Paris and the other one in Brittany, while the third subsidiary is in Canada, near Montreal. So now, back to our topic. Let's start with a short definition. What is optopyrotechnics? An optical pyrotechnic system converts an optical signal into a pyrotechnic initiation. So what does it mean? Actually, intense laser pulses are distributed via optical fibers, patch cords, and here actually optical harnesses, to activate specific events through controlled explosions. To achieve that, the optical pyrotechnic chain must include at least a laser firing unit, LFU, emitting intense near-infrared pulses, generally a few tens of watts, usually in the order of 30 to 40 watts. You need also optical harnesses to route that energy to an optopyrotechnic initiator. So you have here some pictures of products that in this pyrotechnic chain. And on the picture on the right-hand side, I don't know if you can see it clearly because it is quite small here, but this is not the complete initiator product system, but the optopyro initiator patch cord. This part of the system enables to put the optical fiber in direct contact with the pyrotechnic material to ensure the high power density required for thermal initiation. The pyrotechnic material is a compact powder contained in a mechanical part that is not shown here, but that is screwed on the end of the patch cord. So in the group, SEDI-ATI provides the initiator patch cord, while the initiator itself is done by another partner company. SEDI-ATI and Ideal also provide different types of optical harnesses, and Ideal is involved in the laser firing unit. What is remarkable is that optopyro train lines enable long-distance transmission over several hundred meters between the laser source and the initiator, thanks to the extremely low optical transmission losses of optical fibers. Today, optopyrotechnic train lines also include optical safety units. These units are placed upstream of the optical initiator patch cord to ensure the system integrity from arming to firing. So in order to detect in a safe way a default on the optopyrotechnic train line, such as a failure transmission or a weak connection, the company SEDI-ATI has developed an interrogation component consisting of a customizable multimode wavelength division multiplexer, here on the screen called WDM, with specific properties to address this type of application. The WDM can both check the integrity of the complete line with a very low infrared energy control wavelength of a few milliwatts, and it also allows a high power infrared laser ignition wavelength coming from the laser firing unit. This is made possible thanks to a dichroic filter that is directly deposited on the fibers at the heart of the WDM. So you understand that the WDM is wavelength selective. It reflects the control wavelength, in pink here, while it allows the firing wavelength to pass through. So how does it work? The control wavelength is sent into the complete optopyro line. When it reaches the IOP, it is scattered back towards an OTDR, optical time domain reflectometer. Indeed, you can see, maybe barely here, but on the end face of the initiator patch cord, there's also a filter. It's the same as the one inside the WDM, so it reflects the control source wavelength. When the OTDR sees an unusual attenuation of the control signal, it reveals that there is a default on the optopyrotechnic line. The OTDR is able to provide detailed information on the location and overall conditions of splices, connections, defects, and other features of interest. When it is proven that there is no failure on the transmission line, when it is proven that there is a failure on the transmission line, the optopyrotechnic device prevents the ignition wavelength from being fired. And when the control scattered light signature is normal, the laser firing unit is allowed to fire to activate the optopyro initiator. So for ground applications, both the control laser source and the firing laser source can be integrated in the laser firing unit rack. Such a dual laser system is currently being developed at the company Ideal. And in launchers, it's different. The laser sources are much more compact, and usually these are LEDs, and we do not provide that. What is particularly interesting with optopyro technology applied to extreme environments is that the initiation energy is transported as light and not in electricity. And this provides strong advantages over electropyro systems in terms of immunity to electromagnetic environments, as well as in terms of robustness against electrostatic discharge. Also, the optopyro devices bring several safety advantages over electropyro technology by avoiding any initiator premature functioning from electrical disturbance. Another advantage is the reduction in mass and weight compared to electric copper cables used in electropyro chains. In other words, photonics is not just an alternative, it is an enabler under very harsh conditions. Let's now have a quick look at the pyrotechnic applications on the launch pad. So I take the pointer. You see here the yellow part in Ariane 6. These are Ariane 6 cryogenic arms. They are a highly sophisticated ground system designed to withstand extreme loads. They connect the launch vehicle to the launch pad, and primarily they supply the upper stage tanks with liquid hydrogen and liquid oxygen. The main pyrotechnic applications are the cryogenic systems disconnection and the cryogenic arms retraction. The pyro systems must withstand extreme conditions such as the ones listed here. And currently, Fiber Optics Group is not present on the launchpad of Ariane 6, but the subsidiary Ideal has developed both the dual laser firing unit and control source and optical harnesses such as ground for such applications. Now, what about the pyrotechnic applications on the launcher itself? There is something like 80 pyro events in such a launcher. Some are dedicated to functional events, such as ignitions or separations. So these are the green points you see on the picture. And while others allow the flight termination in case of emergency, these are the red points. The company SEDI-ATI has been flying on Ariane 6 since its inaugural flight on July the 9th, 2024. This flight, as well as the following 6 or 7 flights, were all successful. We are involved in the bolded items, that is to say number 0, flight termination, but on the lower stage, and also in number 3, booster separation, and number 5, lower stage separation. At present, only these functions are operated using optopyrotechnics. All the others still rely on electropyrotechnics, but Ariane Group plans to gradually transition to full optopyro. Here are amazing pictures of separation events during an Ariane 6 flight. So you have the booster separation 2 minutes after liftoff and the upper stage separation 7 minutes after liftoff, all realized through optopyrotechnics. To conclude, optopyrotechnics is a key technology for launchers like Ariane 6, enabling critical functions from the launch pad to orbit. Its success relies on the ability of photonics to withstand extreme mechanical, thermal, electromagnetic, and radiation environments. This makes it a highly relevant and demanding application domain for the photonics community. Thank you for your attention.
Thank you very much, Amandine, for this nice presentation. Any question for Amandine? Amandine, you mentioned, the different step where you could use this technology, and where you're still using electronic
Yes.
technologies. What are the main barriers, in using this technology in all applications?
Actually, it's not that there are some barriers, but they do it step by step. They first try to change one step at a time the functions in the launcher to prevent any.
Yeah, of course.
You see.
Problem.
So there's a planning, and they follow.
But there is no technology barriers.
Not as far as I know.
Okay. And another question, with the trend toward reusable rockets, is it possible to use your system several times, or how does it work?
Unfortunately, no. It's one shot, because you create a local explosion. So the part that will explode will be destroyed. But we have we prevent the rest of the electronics and other parts from being damaged, because we work on the hermeticity of the system. So it's only the IOP actually that is destroyed, but you cannot use it twice.
Okay. Yes, Lars, please.
Yeah. Could you say something about the mass saving by going to fiber optics compared to the electro pyro?
Actually, I do not have that data. I cannot tell you, but maybe I can check.
Sure.
Okay, thank you.
Thank you. Any other question for Amandine? Yes, Juan.
I understand that the fibers are multimode fibers. Do you use any optical connector for such a high power, or is always the splicing? How it is connected?
Let me ask my friend Julien. He is also connected and he is a specialist for this and he might have some answers.
Yes. Do you hear me?
Yeah.
Yep.
Okay. Yes, it's with a connector for a special application like Sorio connector with helio contact. On Ariane 6, it's only helio contact with 8G connector for helio contact.
Okay, thank you.
Thank you, Juan, for the question. And if we have another question, thank you again, Amandine,
Thank you.
for your presentation. Thank you very much. And now we can welcome our next speaker, Lars Lierstuen, Head of Space and Business Development at NEO. And Lars, you will present how you came from commercial to orbit, NEO's path into new space, hyperspectral imaging. So Lars, please, the floor is yours. Amandine, can you? Yeah, good, perfect. Thank you.
You see the presentation now?
Yeah, all good.
Good. Hello, I'm Lars Lierstuen. I'm Head of Space and Business Development at NEO. We have been manufacturing hyperspectral images for some years now, and we have started trying to bring them to space. And what I will focus on in this presentation is some lessons learned that may be of value for companies that intend to do the same route. So let's see. I will start with some company background, then list some few challenges, lessons learned, and if time allows, I will also present our space products. We are located in Oslo, Norway. We had our 40 years anniversary last autumn. We are an SME with about 65 employees, focusing on research in electro-optics, and our goal is to develop state-of-the-art products for international market. Down to the right, we have examples of products we have made. Laser gas measurement systems, underwater optical systems, and also these hyperspectral imagers. We are fully owned by a foundation which has a vision to support work in art and physics, and the art part is due to Irma Salveger, who is the widow of our founder. She is 97 years old and still active painter in her atelier in Oslo. We have been designing and manufacturing hyperspectral images for more than 20 years. Our first instrument was sold in 2003. To date, we have sold about 700 instruments worldwide. This is our portfolio. On top, we have our classic systems. Down to the left, we have the Barbero series, and the black ones to the right, that's our drone cameras. We have systems working with CMOS sensors from 400 to 1000 nanometers, InGaAs systems from 950 to 1700 nanometers, and MCT sensors operating from 950 to 2500 nanometers. We are using our cameras on nearly any platform, from lab, airborne to stratosphere, and these days we are working to have our camera in satellite. So a little bit more background. When we came to 2019, we realized that we received a lot of inquiries about modification of our COTS cameras for use on satellites. That was due to the new space area, which already had been present for some years. So in 2019, we decided to apply for funding from the Norwegian Space Agency to see, to see what we could achieve with our competence on hyperspectral imaging. So in 2020, our application was granted. We started designing our first satellite camera, which is the Hyper-Nor. I will come back to that later. And later the same year, NOSA had a call called the ESA-led development project with the possibility of space qualification, which we also applied for and was selected for a Norwegian in-orbit demonstration. That was the start of Hyper-Nor, which was kicked off in 2023. And in 2024, we also established the space as a business area within NEO. Then I come to some challenges, lessons learned. So first, which quality standard? ESA has standards in the frame of ECSS. They cover engineering, design, verification, testing, quality assurance, project management, and product assurance. Our new space customers, they expect delivery within 12 to 18 months. So, and they don't have the, let's say, willingness or the economy to pay for qualification according to ECSS. But something has to be done to prove the reliability of the instruments. So as we see, it's two alternatives: do a tailoring of the ECSS standard, or use components with the established space heritage and proven performance in space environments. We are working according to point 2, trying to use as far as possible parts that already have space heritage. Next lessons learned is about using COTS components for space. That's also a consequence of the desire for low prices. At NEO, we have focused our space activities on instruments working in the E-sphere range from 950 to 2500 nanometers. And the reliability of our instruments is largely driven by the sensor part, the IDCA, Integrated Detector Viewer Cooler Assembly, which in our case is based on COTS components. Since this is the main driver for the reliability, the customer want to require some justification for the reliability of these units. These IDCAs, they are quite expensive, even in the COTS version, from 100,000 euros and upwards. So a large number of samples for testing is not possible. They have to be kept at a minimum. We have to do some environmental testing, for instance, vibration, thermal vacuum, radiation, to satisfy the customers. So the challenges is there are, what if the unit fails in test? Then the customer expects some corrective actions. But since this is COTS components, making modifications is, it will not happen. And if the customer wants added functionality, that will not happen because changing the production line for a few additional sales will not happen. So we are kind of locked there. What we are trying to do is to add shielding to make the unit survive radiation testing and strengthen it as much as we can to have it survive mechanical tests. Next is funding via ESA. It's a lot of funding opportunities via ESA, and this shows our experience with the GSDP and the Hypernor, which we made our pre-proposal in December 2020. And we had a lot of iterations on this proposal based on feedback from ESA. And then we had 5 rounds with tender evaluation boards. So the kickoff was in February 2023, so 24 months after our pre-proposal. So obtaining funding from ESA can be a prolonged and labor-intensive process. Next, stakeholders. Our experience is that we usually discuss instrument sale with a customer, and they focus on instrument performance, price, and schedule. And in parallel, this customer is negotiating with the platform manufacturer. And after the deal with NEO is finalized, the platform manufacturer is introduced to NEO. And the challenge is then the platform manufacturer, they want answers to different questions on a different level than what has been discussed so far. And a significant additional effort is required to support the platform manufacturer. Yeah, we have also started thinking about our calibration validation strategy. There are ground areas like the calibration sites of the radical net, which we think we can use for the Keystone, SMILE, SNR, and bad pixel measurements. But there are claims that the radical net sites are not sufficiently stable. There are seasonal variations. So NEO has started searching for spectrally and geologically stable regions. And we have used data from MODIS and DVI 6.0 and used measurements taken at 2 weeks intervals over 7 years to find stable areas. And the map on the right, you can see red, the red marked areas. They are stable in our first assessment. We have to go one step further with a finer DST to see if it can be used for our hyperspectral images, but that's at least the start. So I think it's typically high altitude deserts, which are very stable with respect to these properties. Then quickly on our space products, Hypernor, I mentioned it several times already. That's our first satellite camera. It's working in the ESV range, 950 to 2500 nanometers. We have focused the design on fine GSD, so we can achieve 4.5 meters from 500 kilometer altitude. It's an MCT sensor, so it's quite few pixels, 640 by 512. That we can use. We have a double slit in this instrument, so we can use a super resolution technique to improve the TSD. Smile and Keystone, they are very good, and also compared to the size of the instrument, we have very good SNR values. And based on this instrument, we can also offer instruments working in with CMOS, so 400 to 1000 nanometers, or InGaAs from 680 to 1675 nanometers. We have also a dedicated methane camera, which we are developing in the frame of an ESA InTube contract. It's working from 1550 to 2500 nanometers. The 30-meter TSD from 600 kilometer altitude, spectral sampling 3.65 nanometers, full width half max 5.48 nanometers, 260 spectral channels. Also a good Smile and Keystone in this instrument. And finally, we have our first flight model. It's not flying yet, but this was delivered last summer. It's really a modification of a classic camera where we have replaced the sensor with a space-grade InGaAs sensor. This is for in-orbit servicing, so it's got a close-up lens 9 to 50 meters. That's all for now. Thank you for your attention.
Thank you very much, Lars, for your presentation. Any question for Lars? So we understood that it was very difficult, to transition the transition from the commercial to the space. From your perspective, what was the most challenging part? Was it to find a phone from ESA, or was it more from the technology side?
I think maybe I came from a company where we made work on contracts for the big industrial primes in Europe, and in those cases you had a list of all requirements you were supposed to meet. But when you are starting from kind of from ground and has to establish the requirements yourself, I think that was very difficult to challenge. Yeah.
The question. And if no question, thank you very much, Lars,
thank you.
for sharing your experience. Thank you. Thank you so much. And now, so we before to welcome you, okay, we have a question from Yoshiaki Shikata. Lars, are you still here? Yes.
Yes, I'm still here.
So what does space-grade sensor mean?
Yeah, in this case, it was a product that already had gone through a qualification campaign via, according to, I would say, old space, ESA old space approach. So going through components were space grade and assembly processes were space grade. Yeah, so it's a very expensive way of. It becomes a very expensive component in the end, and the number of available space grade sensors is very small in my mind.
Thank you, Lars. Again, thank you for your answer. So we welcome. So Roman, are you here? Are you in the room?
Yes.
So welcome, Roman Navaro from Tiny Telescope. So please, Roman, the floor is yours.
Thank you so much, Jeremy, and thank you for your flexibility in scheduling me exactly in this time slot, because I'm traveling and at an airport. Hopefully, I found a nice space where I can quietly present this to you. Anyway, I'd like to present Tiny Telescope. And normally we are busy with building the largest telescopes, both on Earth and in space. So the Very Large Telescope, currently the Extremely Large Telescope, and we built spectrographs for the James Webb Space Telescope. But we also can make very, very small ones, tiny ones. And when we, while we have this technology already for 30 years, we only displayed it publicly on a YouTube video a few years ago, and to our astonishment, this had 2 million views in no time and thousands of comments, which really meant that there's a market out there. And we thought other companies would jump into it, but it's very difficult to achieve a telescope into just one piece of glass. So we founded our company 2 years ago. The technology worked like this. You have one piece of glass and light enters from the left, is transmitted inside the glass, then reflected at the back side. And at the front side in the center, it's concentrated, reflected back to the back of the element, and then it creates a focus with options for filters, dichroics, or other components inside. This is the Zemax ray tracing. And you can see the black lines are the baffles that are inside the glass, so you don't need external baffles. When you make it as compact as we do, all of these 4 optical surfaces, both the transmittive and the reflective ones, become extreme A-spheres. And you really have to make them on the right location and really accurate. 6 times more accurate than for normal lenses, because we use the reflections inside the glass. So the optical surfaces are single nanometer accurate. But once you have achieved this, you have a lot of benefits. So it is very low size, weight, and power. You can take it anywhere. It's the fraction limited performance. And since there's no elements that can move, we can guarantee this. It's temperature insensitive. It works at cryogenic temperatures or extremely hot temperatures. It's extremely robust against launches, shocks, vibrations. And since there's only one component, there's really less testing needed, which is also a benefit for space. And an additional benefit is that it works at an enormously wide wavelength range. So the normal material goes from 200 nanometers to 2.0 micrometers in wavelength, but we can adjust diffuse silica to infrasil or suprasil to go until 160 nanometers wavelength, or all the way up to 3.5 micrometers in the sphere. And we are doing experiments with other materials to see what the performance in the thermal infrared is. The field of view is very small. So compared to the normal field of view of your phone camera or a 50mm lens on a DSLR, it is extremely small. It's about the size of your fingernail at arm's length. But then inside this field of view, we have great performance, and you have full HD, 4K, or even 8K imaging performance. So over here, you can see a broadcasting mast at more than a kilometer length, imaged with an iPhone in zoom mode, imaged in the center with a Canon DSLR and a heavy 200mm lens, and on the right with a tiny telescope. And you see the increasing steps of detail that you can view, well, especially with the tiny telescope. And this is all pictured in this graph, which is a bit complicated, so let me walk you through it. On the horizontal axis, we have the distance. So imagine we are in space at low Earth orbit, 500 kilometers altitude. And then we look for the dotted line, which is the pixel size. And the pixel size goes to 5.5 meters on the vertical axis. So you can do high resolution Earth imaging in a very, very tiny format. For a drone application at, let's say, 100-meter distance, looking at green wavelengths, we can distinguish 2 objects that are only 1.5 millimeters apart. And obviously, in the red and infrared, this performance is a little bit worse, but in the blue and in the ultraviolet, it becomes better due to the wavelength. So at the moment, we have a 125 millimeter, 25 millimeter aperture and a 240 millimeter, 40 millimeter aperture on sale, and the 60 millimeter diameter is still in the prototyping phase. There's lots of applications. Sticking to space first, Earth observation, solar system exploration, going to other planets and moons. It's being used as star trackers and for laser satellite communication, since we can send and receive infrared wavelengths. Also, there's many applications on Earth, including medical imaging, imaging from drones and civilians. And the dream is that someday everyone will have a tiny telescope in their pocket as being part of the mobile phone. So here's a few intelligence, surveillance, and reconnaissance applications, and let me walk you through a few of them. So first, let's start with a satellite. So this is a pocket cube satellite, the smallest standard satellite size with only 5 by 5 centimeters. And this particular satellite is 4 units long, so 20 centimeters long. And even in this small format, we can view an area on Earth of 25 by 25 kilometers. For instance, the port of Rotterdam, as you can see here. And we achieve about 5 meter resolution here with the pixel size. And if we look at that, what we do to simulate these images, because these are still simulated images, we take a high resolution satellite image, and with the PSF that's known to us, we simulate and know what the performance will be of the particular sensor, what it will see. But we can also deconvolve it because we measure the PSF very thoroughly before launch. And using this information, we can achieve a higher resolution than the initial sensor sees, so we can see more details. And this is an actual implementation of the tiny telescope in four different tiny telescopes in a 1U size nanosat. And all the 4 telescopes have a slightly different pointing, as you can see on the lower left. And every 3 seconds, you move this by about 25 kilometers. So you'll be able to image, well, the whole Earth, or a whole Earth orbit in 1.5 hours. If you launch 26 of those satellites in a single launch in a sun-synchronous orbit, this means that every 3.5 minutes, one of these satellites will pass the equator. And in 3.5 minutes, Earth has rotated around 100 kilometers. So with 26 of those satellites, you can do a daily global imaging at 5 meter resolution. Other applications. Okay, so this is not space, so I'll go quickly through it. This is a HAPS, a high altitude platform station, the Airbus Zephyr. It's a plane with covered with solar panels, and when it's launched, it can stay up at 20 kilometers altitude for weeks or months, but it has only 5 kilograms payload, and the tiny telescope is an excellent part of this payload, leaving room for other applications. So at 20 kilometers altitude, you can view instantly 1 square kilometer with about 30 centimeters resolution, meaning that you can follow everyone who's walking downstairs. Also applications on drones, and this is an even smaller version. On drones, it's really important that you have a good gimbal to suppress vibrations and to also point very accurately where you want to look. And this particular camera telescope combination is only 50 grams and 32 millimeters in diameter. And from 0.5 kilometer distance, so out of sight and out of hearing range, you can still identify people and see what they're eating, for instance. This is actual pictures taken with a tiny telescope. So on the right, we see a climber climbing a wall, and you can barely make out the climber on the normal picture. taken with a phone or a DSLR camera. And on the background, you see the climber enlarged, and you can see with a tiny telescope even the details on the shoes. This is a radio telescope at our premises at 100-meter distance. Left the normal field of view, right the tiny telescope field of view, and even the dish that has 5 mm spacing of the reflectors. You can really see that clearly with this tiny telescope. Another example is this fishing trailer. I hope it's visible because I'm not sure how well the video transmits. But from a distance of a few kilometers, it was absolutely impossible to see all these birds. But the tiny telescope makes them visible, even at low light applications, such as over here in twilight. And I'm not sure why. Yep, here it goes. This is a fun fair at 21 kilometers distance, where you can see the fun rides going clearly. And I must say, this video that is probably transmitted at maybe 1K image quality. The original image quality is 4K, so pretty accurate. At the SPE meeting in Madrid last September, this is remote sensing. We had a booth together with people from QDI Systems, Quantum Dot Imaging, and they generate quantum dots and they spray that over normal silicon sensors to make them sensitive to the infrared wavelengths. And we had a live demo over there where we viewed in infrared, in short wavelength infrared, in this case, some scene outdoors. Other applications with cameras include this Qbert system. This is a system with only 300 by 300 pixels, but then every pixel has 52 different colors. So what you see over here is a false color representation of the canopy of where we can look at individual leaves and search for illnesses in the plants in the forest. We are negotiating with ESA about applications for the Enceladus mission, where a possibility is that this larger version stays on the orbiter, orbiting Saturn and its moons, and the smaller version will even land on the surface of Enceladus and will be searching for life in the water oceans below this ice. This is the application as a star tracker. So on the left, you see an image taken of the night sky. And on the right, these are the stars that are recognized, where we know the positions. And because of the large zoom factor, the large enlargement, we can really accurately determine the position of a satellite and the pointing of the satellite. And we're looking at the performance 10 times more accurate than standard star trackers. But then this is a very small version. I mean, there are larger star trackers with the same performance, but they are really large and with a mass of about 5 to 10 kilograms. And this is really a tiny unit. We have, on top of that, also the possibility to do telecommunication, sending and receiving infrared wavelengths. And I'd like to conclude by saying that our team, although we started only 2 years ago, is really expanding. We have 20 plus staff at the moment. And just a few months ago, we had the opening of what we call the Tiny Factory, so a dedicated facility where we manufacture the tiny telescopes. And for testing, we do that at ASTRON, Space Research Organization, Netherlands, but also at ASTRON and NLR. So other facilities that we use. And we recently also opened a sales office at the ESA Business Incubation Center in Noordwijk. We try to be very active at various conferences and exhibitions, where you can see that we have a booth, for instance, here in Bremen at the NL Space booth. And some highlights and news for this year. So we expect our first launch to be happening in September this year. We recently started a medical application for eye care with improved accuracy. Drone tests are being planned and maybe even being done today. And we have some new patents that will be also filed this year. So lots of things are happening, and I'll take any questions that you have.
Thank you very much, Roman, for this presentation and this overview of your technology. Any question, Roman? So when you mentioned your first launch, it's related to space, right?
Yes, that's our first launch to space. Actually, it will be a resupply mission of the International Space Station,
Right.
and it will be launched from there.
Okay, very nice. And how much space topics are important for you? Because you mentioned at the beginning, consumer market, space market.
Well, space is where we have our heritage and where the performance at extreme temperatures and under extreme conditions with vibrations and shocks are really important. So that's really our main market at the moment. And we are now expanding into different markets, including drones and medical applications.
Okay, and what would you need, from the participant today? Are you looking for something special?
Always, of course. So we are looking for people that want to use high resolution or Earth imaging or other applications in a very small and lightweight package. But there's always combinations of technologies possible. For instance, with UV or infrared or shortwave infrared detectors. So we are really open for combined applications.
Okay, and you can adapt your system on any kind of technologies, any kind of imaging system.
Yes, and with Dichroics, we can, for instance, have a visible detector and an infrared detector at the same time, and do broadband multispectral hyperspectral imaging.
Okay.
Yes.
Any question for Roman? And if not, bye-bye, Roman. Have a nice flight.
Thank you so much. I'll be running through the gate now. Thanks a lot.
Bye-bye. Thank you, Roman. And now we can welcome our next and the last speaker of the day, Juan Barbero from Alter Technology Group. And Juan, you are going to talk about testing photonics for space alter photonics area. So please, the floor is yours.
Okay, so you hear me and you see the slides?
Yeah.
Okay, so I'm going to talk a little bit about alter technology and our experience in testing photonic components for the space application. So basically, alter technology is a laboratory, let's say. So we are doing tests for the space applications mainly. We are a single point of contact for high reliability testing of electronic, and I work in the Optoelectronic department. So my group, or the group where I belong, is focused on testing lasers, photodiodes, anything related to photonics for space. Talking a little bit about the space environment, the previous talkers have talked a little bit about it, but when we talk about the space environment, we have to take into account extreme temperatures sometimes. It is not only the satellites that can be in the shadow of the Earth, for example, the temperature can drop and rise quite fast. Vacuum is also there, and that makes the dissipation a lot of difficult, and that creates a lot of issues with heat transfer in one part of the satellite that's, for example, illuminated, and the other part that is in the shadow, and so on. Of course, radiation around the Earth is important, but for example, radiation around Jupiter is extremely high, not because it is near the sun, because it is a lot farther than the Earth, but because of the great magnetic field that Jupiter has, and that traps a lot of charged particles, creating a very huge radiation and horrible environment. As mentioned before, the launch vibrations and the pyrotechnics for opening the fairings and the different stages of the rockets are really important. And then, which is really important, is that there's no maintenance up there, with the only exception of, as everybody knows, of the telescope, of the Hubble telescope, and you need then to work the systems to work for a long time without any maintenance, and that is of course very important. So regarding our experience in optoelectronics, we have tested a lot of, we are testing right now a lot of lasers and LEDs, receivers, meaning photodiodes of any type, optical transceivers, amplifiers, modulators, switches, splitters in fiber and no fiber, optocouplers, liquid crystal devices, image sensors, talk a little bit about that. And we are starting doing things in photonic integrated circuits that are, everybody talks about them. Space needs, let's say, reliable components. That means that we are not state-of-the-art many times, but we need components that are let's say reliability is very high. So for that, photonic integrated circuits is a very interesting topic, but we are not there yet. Regarding image sensors, we are testing a lot of image sensors. We have a small clean room, and we can do, let's say, any characterization of the image sensors. We can develop our own electronics, so we call it the camera, to take the pictures, to read and record the pictures from the image sensor. We do all the space environmental testing related, so then vacuum, humidity is for the ground equipment, but also important for space sometimes, and radiation of any type, total dose. We have our own total dose facility, but we also travel to do this membrane damage to Belgium normally, or single events also to Belgium or to Finland or wherever we need to go. In temperature, and that's quite important, we have a lot of thermal cycling chambers. We can right now go from 10 Kelvin, so minus 263 degrees, to more than 400 degrees. We are testing a lot of components for around 40 Kelvin for Ariel mission that is going to be observing, trying to locate exoplanets and so on. For whatever the reason, the electronics is going to work at very low temperature, and we're testing a lot of components at that temperature. We can do that also in vacuum, so that's important. And we also like to do combine, or like to do, sometimes are requested to do combining tests, and we don't say no. We say to our customers, give us some time to study how to do it, and we will propose probably something to you for doing it. So you have some exchange, let's say, test to do combine, for example, temperature vibration or temperature and radiation, or wherever you need. That is difficult to find. We were open to collaborate to create a custom solution for our customers. Focusing a little bit on temperature and vacuum and mechanical. We have something like 10 chambers. I think it's even more. It's more. They are like micro ovens. You see here the picture that can cool to minus 190 more or less and heat to more than 400 degrees with very fast temperature rate, which is also sometimes important. They are small, so we use it for components, and we have a different kind of thermal vacuum systems. As I say, we have an helium cryostat, a couple of helium cryostats actually, that can cool to 10 Kelvin more or less, so around minus 163 degrees. We have a standard, let's say, vacuum systems that are not too big. The biggest vacuum that we have can be used for samples or little system, or even CubeSats up to 55 by 55 by 55 centimeters. And we have even smaller vacuum systems that can be placed inside our climatic chambers. And with that, we prepare a custom system that we can do thermal vacuum from liquid nitrogen temperature from around -190 to at least +200 degrees, because we have never tried to go higher in vacuum. But the good thing about our small vacuum chambers for this is that the site is quite small, and that means that the price is also scaled down. Let's say if you compare to the thermal vacuum, huge thermal vacuum systems that are available at the STEC, for example, or different agencies. So our prices are a lot lower for that thermal vacuum in the stream temperatures, which is, I think, quite a unique solution. And for mechanical tests, we have shakers and a simulator for the SRS to simulate the Spirosoft systems. So we do that also. And just to finish, some real examples of things that we have been testing. And I am going to show you 3 examples of, let's say, old projects, things that we have done, but we did it some years ago. We work a lot on the Curiosity rover environmental monitoring station that is monitoring the weather on Mars, and we did a lot of tests of the photodiodes, integrated circuits, wind sensors, and so on. These are the photodiodes that are directly looking at the sky in Mars, checking the ultraviolet light. They are exposed, totally exposed to the atmosphere. So we had to check that they work properly from -135 degrees to more than 100 degrees. And we did thousands of thermal cycling to check that they can behave correctly. Then there are some thermopiles to measure the temperature of the ground on Mars using these thermopiles, and they are looking at that. And NASA is using this environmental station to check if the weather is, let's say, good enough to work, and then to start drilling something on a rock that they want to analyze, or to move the rover and so on. So it is working quite well. I took this picture some days ago on the 9th of May, as you see here, and it's still giving the temperature, the air temperature, the ground temperature, and so on. So it is being working for around 4,900 sols of Mars, and it's still working. And there is a new version of this in the next rovers. And for example, something that is traveling to Jupiter right now is JUICE, is to study the moons around Jupiter. And as I said before, the radiation environment there is terrible, and the temperature is also quite terrible. We did a lot of tests, fibers actually, and connectors, optical connectors, that are going to be mounted in this boom that is to measure the magnetic field. They need to measure the magnetic field with very good accuracy. You need to put the magnetometers far from the electronics of the ship itself. So there is this boom. There is a long, let's say, long stick where you put the magnetometer, and then your signals are sent back through fibers, and those fibers are multimode fibers, are going to be exposed to the temperature outside the ship. So there was a study saying that a part of the connectors were going to be around -80, some other connectors were going to be around -160, and some other were going to be at -190. And we were requested to do a thermal cycling from these very low temperatures to high temperatures simultaneously on 3 different areas, and we proposed this combined setup of climatic chambers coupled one to each other with some lasers and photodiodes measuring and plotting. And we also needed to do a radiation of the fibers at very low temperature. So we use an helium cryostat, radiation at the same time. Actually, this time we didn't do it ourselves. We went to Fraunhofer Institute in Germany, but the idea was to use an helium cryostat and to place the cobalt-60 source in between a coil of fiber that was in vacuum, and then measuring from outside. We will do it now ourselves if we have to do it again. And just that the oldest, I think this is a satellite that launched in 2009. It was the first satellite, at least in Europe, using lasers, fibers, and detectors. It is still running. It is still operational. It is measuring the soil moisture and the ocean salinity. I remember this. I didn't remember it, but in the next IXO symposium, I have seen that Nikos Karafolas, that is probably known by all of you, he will present the status of this mission, saying that it's still running. And I remember, for example, this exchange test that we had to do, because the panels with the lasers and detectors were ready during the launch, and they were unbended in space. And for that, we were requested to do an unbending of the fibers at very low temperature. We had to bend and unbend the fibers at around minus 60 degrees Celsius. So we designed something, and we did that test while monitoring the optical power going through the fibers. It was interesting. There was variations during bending, and the most interesting thing is that a very flexible fiber become very rigid at minus 60 degrees, and the force to bend it was really strong, but it was not broken. It was working well all the time, even if it was really hard to bend. So it was an interesting thing that we did alone, as you can imagine, before the launch. So we did that in 2007 or something like that. So there are very strange things that we have done. And that is a summary of my presentation. I wanted to say that we are dealing with the space environment continually. It's our work to do testing for a space environment. In the optoelectronic area, we are really willing to do interesting things and to collaborate with our customers, developing complex setups or helping them to do whatever is needed. Of course, we are open to do the standard testing of lasers or photodiodes or whatever, and the more the better. But we are not close to new challenges and developments in collaboration with our customers. I think that is really appreciated by some of our customers, because it is difficult to find a place to do that. And that's it. So basically, you have any questions, you can ask now, or you can send me an email, or if you have a request of quotations, that is the email for it. That's it. Thank you.
Thank you, Juan. Thank you very much for your overview and presentation. Any question for Juan? Juan, with the new space demanding faster and also cheaper tests, how did you, or how do you adapt your offer to these new requirements coming from new space?
Yeah, new space is interesting because we were used to, let's say, the standard space where the number of samples to test is normally very low. Every scientific mission is doing a complete 100% testing of any component that is going to fly, and that is what we were used to. But new space is dealing with thousands of satellites or small satellites with a limited budget. So we are doing a lot of things for new space. Sometimes we propose to a customer that has a limited budget and they want to be sure that their small satellite is going to work at least for some moments. So we propose tailor space testing flows, reusing samples, reducing the number of samples. We can do a lot of things for our customers, near space customers, or for example, we have received thousands of components for a constellation, and we are testing some of them or doing a particular fast characterization of some devices, and then a deeper characterization to some of them, only to save time. So things are changing. The complete, let's say, testing for scientific missions will continue, because scientific mission is something that you cannot risk. But the new space is changing a lot of the way we test. Yeah.
And so we have two questions. One comes from the chat from Sumitomo Electric Tokyo, Yoshiaki Shikata. The question is, do you have space radiation effect testing facility?
We have our Cobalt-60 facility is a public institute called CNA in very near our headquarters, but it was mounted by Alter in collaboration with them. So we have total access. We control the access to the facility. So for Cobalt-60 gamma radiation, we have our own, let's say, facility, in the sense that we control it. And we have different areas for different doses, and this we have let's say 100% sure that there's a space for doing testing tomorrow if we need it. And then for protons or single heavy ions and those kind of things, we go to external facilities in Belgium, in Finland, in Netherlands, wherever. Depending on the availability and so on, but like anybody, let's say.
Thank you. And a question from Mirvais.
Could you unmute? Thank you. Mirvais, first of all, the pronunciation. Thank you. Good try. Hey, Juan, a very nice overview. I have a question about, because I saw that you also do PICs and lasers and these kind of things. This is just a feeling question rather than technical. What's your feeling on epoxies and the usage, and what do you propose to the community?
On the use of epoxies for packaging, for example.
The packaging industry, for example, in photonics is basically built around epoxy, especially because of the different type of materials that has to be combined, from indium phosphide to gallium nitride even sometimes. But for space, that's of course not the best approach. Do you have any feeling, advice moving forward?
I would say, okay, there are really good epoxies over there. There are very good glues that are used in space applications for photonics and so on. But I agree, it is not normally the best option. There are people doing, for example, soldering of Optikk devices, glasses, lenses, micro lenses that are soldered. You know, the people from the Fraunhofer Institute, for example, do a very precise soldering of optical devices. We tested some lasers manufactured by a company called Monochrome that are used for Raman spectroscopy that were packaged in a small package. It was a metallic package around 5 centimeters long and 3 centimeters wide that had a lot of lenses, splitters, I mean the crystal splitters and so on, that were soldered actually, because what they do is that they create a metallization of around the crystal, and then the metallization is soldered to the precision. So there are solutions there, but I wouldn't say that epoxies are not going to be used. There are very good epoxies that are used in fixing the components, and I think they are validated for space applications with very low gassing, no problems of that type. So I wouldn't say that it is going to be the epoxies are going to be, let's say, not used. I wish probably they will continue being used for a long time.
Okay, thank you very much.
Thank you. Okay, so if you don't have any other question, thank you, Juan, again for your nice presentation. I would like to thank all the speakers of this today's event. I hope that you learn some things, or you get good connection, and feel free to to reach out me or any member of the Optikk team if you want to be introduced to someone here And I would like also to thank, of course, our sponsor of today's event, Photon First. So thank you again, guys, for sponsoring our event. And yeah, you have a poll now to answer. So please take a few minutes to answer the poll. And then, yeah, I would like also to add in the chat the link to our event at AIP. Feel free to click on the link and check our webpage of this event. I think that it could be very interesting for you to attend. We'll cover these topics, of course, but also other kind of topic. And it will be a great event. So thank you again to all of you, and see you to another epic event. Thank you very much.
Thank you. Thank you,
Bye.
everyone.
Thank
Bye.
you.
Thank you. Bye bye.